Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Dagster offers a new approach to building and running data platforms and data pipelines. It is an open-source, cloud-native orchestrator for the whole development lifecycle, with integrated lineage and observability, a declarative programming model, and best-in-class testability. Your team can get up and running in minutes thanks to Dagster Cloud, an enterprise-class hosted solution that offers serverless and hybrid deployments, enhanced security, and on-demand ephemeral test deployments. Go to dataengineeringpodcast.com/Dagster today to get started, and your first 30 days are free. Data lakes are notoriously complex. For data engineers who battle to build and scale high-quality data workflows on the data lake, Starburst powers petabyte-scale SQL analytics fast, at a fraction of the cost of traditional methods, so that you can meet all of your data needs, ranging from AI to data applications to complete analytics. Trusted by teams of all sizes, including Comcast and DoorDash, Starburst is a data lake analytics platform that delivers the adaptability and flexibility a lakehouse ecosystem promises. And Starburst does all of this on an open architecture, with first-class support for Apache Iceberg, Delta Lake, and Hoodie, so you always maintain ownership of your data. Want to see Starburst in action? Go to dataengineeringpodcast.com/starburst and get $500 in credits to try Starburst Galaxy today, the easiest and fastest way to get started using Trino. Your host is Tobias Macey, and today I'm interviewing Oren Eini about the work of designing and building a NoSQL database engine. So, Oren, can you start by introducing yourself?
Yes, so I'm Oren. I'm the CEO of RavenDB. I've been working on databases for about 20 plus years. I've been working on RavenDB specifically since 2007 now, so over 15 years at this point. RavenDB is a document database. It's written in .NET and run on everything from a Raspberry Pi, Linux, Windows, cloud, and edge deployments. And that's about it. That's the elevator speech.
And do you remember how you first got started working in the data space?
Completely accidentally. I was looking into building some business application, something that I wanted to do for myself. I think it was a feed reader at the time where RSS was king, and I needed to persist some data, and I started using an object relational mapper. And then I got really interested in how it works and what's going on. And eventually ended up being a contributor to the project for the Inhabit project in .NET. And that has been my life for about 5 or 10 years, where I got really deep into that, how database work, how they're operating on a, how they operate over data, how it's reflected to your application, etc. It was also a time that was incredibly frustrating to me because I understood how database work, but I kept getting queries from people and requests for assistance that did some pretty horrible stuff. I love saying that at one point I went to a customer and I consulted on a performance problem that they had, and it appears that they were running over 17,000 queries to load a single page. And you look at it and says, I don't even know how to even start telling about it. There is a statement that I that this is not even wrong. This is just something completely different. And so I did it for a while, and at some point I got really frustrated with seeing the same sort of errors over and over again. So I decided that I'm going to do something about it, and I wrote an automated tool that would basically look at the interactions between your application and the database and analyze what's going on. Now, a profiler for databases is absolutely not something new. But my point was, I don't want to try to analyze a specific query. Oh, you need indexes here, you need indexes. I want to analyze the entire interaction between your application and the database, seeing how, oh, you load this data multiple times, you're talking too much to the database, those sort of things. Relatively simple things, all told. But the amazing thing about it is that the amount of things that it found and the level of impact it had was huge. And that led me even into more deep holes of people who got burned working on complicated data projects. At that time, we're talking relational databases were almost the only game in town. NoSQL database were just getting started. And I remember looking at CouchDB and going, wow, like I really loved that idea. It clicked, it made sense. And then I looked into what it actually took to run it. And it was somewhere slightly beyond black magic and blood sacrifices. You could do that. You could get it working. And if you got the planets to align just right, it would even work. And then, you're in a position where you're juggling knives. And it's absolutely amazing until you sleep, and then you have to pick up your fingers from the floor using your own teeth. Uh, and that was, I remember being really upset about that. It was like, here is something that's finding me, and I cannot make use of that. So I had this idea. Here is this database that would be perfect. And it's funny because I've been now working on databases for a lot of time from the perspective of the person who built database engines. And what ended up happening is that I sat down and thought about how a database should look like from the other side, because I was primarily then a application developer. So what are the sort of features that I want? And some of them are so stupid. They're so simple and stupid things that drive me crazy. One of them, for example, let's say that you want to show a page list. What do you need in order to actually render a page list to the user? You want so give me the first page of the items and give me the total count, so I can show you how many items you have there. It turns out that this is incredibly expensive. Why is that? Because you have to actually execute the query to run all of the results and sort them, get the right value, and then you have to do it all over again just to get a count. So select top 10 from and then select count from. And that's actually, it sounds silly, but let me drop you down to what actually happened here. On the first hand, let's say that you have a non-trivial query. So you have to execute this non-trivial query twice. The other thing is that let's say that you're running on the cloud or the network database or something like that, and you have network latency talking to the database, even if it's just 2 to 3 milliseconds. Now you're spending 6 milliseconds just on network traffic. And when I designed RavenDB, one of the things that I did was, here is this small feature. Let's ensure that whenever you ask for the first page of the results or for a page of results, I will also give you the total count already there. There is no extra cost that you have to do that. So, okay, I saved the query, which is nice. I also saved the network boundary. And that's just like this tiny, small detail. Oh, I don't need to worry about this anymore. Wow. Yeah. So it just went up.
As you said, there are a lot of things that seem silly as the user of why is this so hard? And then you start digging into the implementation details and you say, oh, it makes sense that as to why it's so hard in this case, but it shouldn't have to be that way. You mentioned the juxtaposition of relational database engines and NoSQL engines. And for purposes of this conversation, we want to talk through what it means to actually design and build a NoSQL database. But before we can get into that, I'm wondering if you can just first give your definition of what constitutes a NoSQL database.
I would want to correct something, not NoSQL, but non-relational. And the reason for that, SQL as a query language has absolutely won the day. There is, I believe that the only database right now, only popular database right now that doesn't have a SQL variant is MongoDB. And I don't know why they do that. They still do that. It's not complicated and it's so much easier. But if you look at relational versus non-relational databases and go back, 40 and 50 years, then it used to be database wars. There used to be this scenario where You had to select which database you want, and there was navigation database and flat-file database and all sorts of stuff like that. And relational database just won the day, and it won the day so conclusively that in many respects, databases today are relational database. And if you want to say I'm a non-relational database, you have to explicitly say that. And that lasted for close to 30 years, which is an amazing time frame, especially when you start talking about the speed and velocity of software development. And it turns out that two major things happen to uh, invalidate or shake the foundation of the database world. And one of them was the internet and the working in distributed environment. And the other thing was the amount and the scale that we worked on. And it's funny because to a large extent, a lot of that was actually driven by hardware problems. If I'm going to the early Google or any of the big web properties of the early 2000s, one of the primary issues that they have to deal with in terms of data sizes was physical limitation of the hardware. You're using HDDs, hard disk drives, and if you had a really good one, you had 10,000 RPMs, which means that at the best case scenario, you have low hundreds of times that you can read or write to the disk, which is okay. If I want to support more than 500 reads per second from the disk, I can literally not do that. I have to get two disks, and that led to basically splitting the data across multiple machines and commodity hardware and something like that, which then led to a really interesting problem. Now you're running in a distributed environment with everything that this entails. So let's say that the simple example I can think of, let's say that they have employees that are spread over multiple multiple nodes in a sharded database, and I want to ensure that they have a unique username. Well, how do I do that if I have to deal with some part of my system may be unavailable or something like that? So, or how do I handle foreign keys in a distributed environment? Those are all really hard problems. And another aspect that we have to deal with is the amount of complexity that you look at in terms of the data. If you're talking about something that used to be very simple, let's talk about a shopping cart. Well, a shopping cart used to be here is the name of the person and here is the product that they purchased and maybe the amount. Nothing really that interesting. But it still means that if you want to render the shopping cart for a user, you have to touch 3 or 4 tables. Okay, that's reasonable, except that if you now have, you don't just have a shopping cart, you not just the items. Here are the offers and sales and recommendations here to other people bought, and did you mean to buy this and that. For each one of the products we also have to run analysis on allergens, and this is organic or non-organics, and I'm vegan or not vegan, a whole bunch of other stuff like that. So the amount of complexity they have to deal with is really high. Now let's talk about how do I, as a user, want to be look at my shopping cart and see, does it contain gluten, yes or not, for any one of my items? Well, that means if I'm working on a relational database, 2 or 3 additional queries per item in the shopping cart, just because I'm using a relational model and the data is spread across multiple tables, leaving aside things about scale and size and everything like that. So the cost of complexity of building systems using relational systems increase in a very rapid fashion. And that is something that is very easy to ignore until you go from your development machine where you have small amount of data, single user, and not a lot of traffic, and you push it to production. Suddenly you look at your database and, oh, I'm doing 100,000 queries per second, and I don't even understand why. But my Amazon RDS bill is through the roof because of that. Non-relational databases, and we have everything from key value like Redis or document base like RavenDB, to graph databases in Neo4j. They take very different models into how you operate them. So you also have databases such as Cassandra or other column family databases where the amount of data that you have is stupendous in the hundreds of terabytes, multiple petabytes, and then you realize that, okay, you're now back to first principles. My data is spread over 200 or 300 servers, and I have to be very careful about how I orchestrate and model things, because I cannot do just a random query over a petabyte of information. Not if I expect to be able to return results within 100, 200 milliseconds to the user. Today, and I'm talking about today versus what we had 15 or 20 years ago, I think that the primary difference between relational and non-relational databases is in the way that you model the data, whatever this is, in tables spread across many different locations, and the sort of operations that you can run over this data, and the distribution and management model. This is really interesting because if I'm looking into document databases, this is near and dear to my heart. Obviously, I've been working on it for a long while. Then you can look into, okay, at the core, a document database is just, okay, here is a bunch of JSON file, XML file, or something like that. Well, I remember using SQL Server 2005, it had XML columns. I made an extensive usage of that back in the day. And right now, I don't believe there is any relational database that doesn't have some support for doing JSON values. So what's the difference between those? Well, the difference is between, I have some JSON text or JSON values that I can operate on to some level, and but still the entire system is based around rows and columns. For example, if I have if I want to store user document in a JSON value inside of Postgres, then trying to ensure that I have a unique username inside that JSON value is not something that you want to tackle. Certainly, I don't know if it's possible. Last I checked, it was not, but I'm not an expert in that. But even if it is, it's really, really complicated. Defining things like indexes or aggregation over those values is also really complicated. And there is another aspect that is almost accidental here. A relational database, almost by definition, means that you're running on one server. If you're running on, I want to run a cluster of servers, then, in all cases, it's going to be, I have a primary and secondaries, and the secondaries are only used for read replicas. And if I'm really, really smart about it, I'm going to do a automatic leader election. But this is not but relational databases are very strongly focused on there is a single source of truth and it moves between those each and every time. If you're trying to deal with network partitions or any sort of items that you run into production, it's very easy to get yourself into really bad situation. I have a really good example here, which is GitHub in 2018. They were using, I believe, MySQL at the time, and they were running in multiple clusters in the West and East Coast, and they had a primary node that accepted all of the writes. And at some point, they have a 43 seconds router failure, which trigger a automatic leader election and move the primary to a different node. I think it was actually went to the West Coast data center instead of the East Coast data center or something like that. And suddenly you had, but that was a network partition. Some other nodes in the system did not get this notice. So what actually happened was that you had nodes that were writing to different primaries at the same time. So we're talking about 43 seconds of network partition, and that led to GitHub being down for over 24 hours. And the postmortem that they publish afterward reads like a thriller, basically, in the sense of, we have to do this, we have to do this. Eventually, they had to reconcile transactions by hand, as insane that sounds. So when we're talking about relational databases, I think that the way that you work with and the manner in which you operate are very different. If I'm looking at RavenDB specifically, then a lot of the operations are explicitly meant to be. The idea here is a database is a grown up. You don't need a babysitter. You don't need someone to continuously monitor and wipe its nose and something like that. A great example that they have here is that query planning in databases is complicated. Complicated to the level of multiple PhDs in that area over decades of work. So this is not nearly done. And as a user of a database, you're expected to be able to make good use of that and define the appropriate indexes and all of the trades of and something like that. And if you change your query to the most minuscule degree, well, it may use a different query plan and suddenly your entire system is down. Whereas with Raven, for example, one of the assumptions that we make is that I don't have a babysitter. I don't have a fully trained DBA on call to run over everything. So you run a query, and there are two responsibilities for the query optimizer inside of RavenDB. One of them is to actually generate the optimal query plan, but this is what every database tries to do. But the other one is to detect when I don't have a good query plan. And then what I want to do, I want to be able to generate the appropriate set of indexes and operation, change the structure of the database itself in order to handle that. And that leads me to something that is funny. When we talk about relational databases, people tend to think about the actual relation, tables and columns, but there is a much bigger problem in the way that you even think about the operation. Let's talk about something as simple as a shopping cart, and let's think about how it works. I have a shopping cart. I want to add an item to the shopping cart. So I look at the product page. I click add. Then it goes to some API endpoint. It loads my shopping cart. Add it if the value is already in the shopping cart, or create a new line items, or increment the line item if it's already there. And okay, that's great. But then I move to actually going ahead and purchasing that order and purchase shopping cart, etc. But if I'm looking at the actual interaction between my application and the database, it turns out that the situation is a lot more complex, because I have this API endpoint that got this add a new item to the shopping cart, and now my API starts to have a chat with the database. Can you give me this? What about this? I want you to modify this, and eventually go ahead and commit the transaction. And remember what I said earlier about network bandwidth being a meaningful impact. Relational database were designed at a time where things were a lot slower. The number of people were a number of users in the database were minuscule. The amount of data that we work was less, and most of the time we were working in the same location. So the network cost of going over the network tended to be far less costly. So you had this idea of, okay, I'm going to begin a transaction, ask the database a question, wait for the user to actually look into that, and then make decision if finally I'm going to commit everything. But this is not how we do things these days. We are doing that in distinct calls using a request response API. So there's no underlying transaction that encompass my process of purchasing something from a store or something like that. It's a set of discrete operations. Now, when it comes to translate that operation, the idea of having a chat with the database and doing this back and forth versus the model that RavenDB uses, which is the batch transaction model, where the client side is going to aggregate all of the changes that you want to do and then send all of them to the database in one shot, means that you get a vastly reduced amount of network traffic. I think that looking back, one of the biggest and most important design decision that we made was to decide what sort of guarantees do I want to provide to my user. And by being able to reduce the sort of guarantees that I need to do, I was able to dramatically simplify the overall design and implementation of the database while being able to offer a lot more features to the end user.
That was definitely a great overview of all of the different considerations in non-relational engines. And I think another interesting aspect of this space is, to your point, of most of these engines do have a SQL interface now, whereas at the outset, when non-relational engines first became a popular choice, they've been around for decades, but they really started to take off as a class of database engines around the 2009 2010 timeframe. I think, sure, people debate the timing a little bit, but roughly in that area. And I'm curious how you have seen the user requirements around non-relational engines change over that time as they started to realize that maybe they can have their cake and eat it too, and not just say, oh, well, if I'm using a non-relational engine, then that means I have to give up on the idea of transactions, or I have to give up on the idea of being able to
Oh,
query in
wait,
SQL,
don't.
etc.
Okay. No, 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 no. Hey, this is. Okay. I'm sorry, you just hit a big red blinking button. Transactions are important. Like, I don't understand how you can build a database without transactions. And the moment that, again, going back to my example of a shopping cart, I want to add an item to the shopping cart and maybe modify some details about, oh, this is my favorite product ever, whatever. And I want both of those things to go to the database in a single unit. If I don't do that, then somehow I need to maintain consistency in my application. I had the dubious pleasure of implementing multiple transaction systems, and needing to build something that in application code is absolutely insane. Most of the databases, most of the non-relational databases, especially in the 2010 timeframe, did not have transactions. They are complicated, they slow things down, and the things that NoSQL databases most wanted to do is, let me show you how fast I can go. I think that over time, two important things happen. One of them is hardware change. If in the early 2000s we have hard disks, then we move to SSDs and now to NVMEs, which means that I'm able to provide, 200,000 writes per second. Yeah, I can handle that. I have the hardware to support that. You want to handle million reads per second? Yeah, no problem. Give me enough network bandwidth, and we will deal with that. So that meant that a lot of the barriers that made, oh, how can I implement write transactions properly in performant manner, became a lot simpler. I remember at one point I was running performance benchmarks, and I was trying to compare SQLite, Firebird, and I think LevelDB or something like that. Talking early 2013-14. And I think that Firebird did not use fsync. And to people who know about databases, that means that it cannot actually be durable. And I remember looking at it, and that's not possible. And then I looked into how SQLite did that, and SQL use fsync, and LevelDB use fsync. And I was looking at another database called eSent, which is an embedded database that comes with Windows. It's now open source, and you can look at the code. It's really interesting. And I remember SQLite was the, 200-300 transactions per second, LevelDB around 150, 200 per second, and eSent was at 20,000 per second. And I could not even understand how this is possible. At one point, I'm looking and I'm tracing the the system calls, and I realized that, oh, it doesn't use fsyncs, it uses direct IO. And I remember implementing similar features afterward when we built our own storage engine, and implementing something called transaction merging. So you have multiple writes to the database of multiple transactions that are being aggregated and sent in one shot, and the performance jump by about 15 times faster. So the requirement from the users is you cannot give up transactions anymore. This is not. I want to be really fast. I want to have all of those sort of things, but I still absolutely expect you to give me mandatory features like transactions. For queries, there are now options. I want to be able to throw my data here. It should be fast, but I also want to be able to operate on that on all sorts of interesting ways. Another aspect that is really interesting is, again, going back to the hardware. I can go and buy an 8 terabyte disk for a few $100. Enterprise edition with, you know, with trade and everything wouldn't break the bank. And if I want to, I can go even higher. And that means that I'm no longer constrained by what I can do on a single machine. Not only constrained about what is possible, my CPU is a lot faster, so I have a lot more available capacity, and that, I think, very justifiably so, is translated into two things. First, we are much faster, and the other thing, the users aren't willing to accept driving uphill both ways in order to achieve their performance goals.
For teams who are doing the calculus of choosing a relational versus a non-relational engine, I'm curious what you see as the major factors that push them in one direction or the other, and in particular how the underlying data model might shift that decision making, where maybe they're used to tabular representations but they need graph for being able to do relational traversals, or they are interested in being able to use the document store, but then they're concerned about being able to join across different collections. Just wondering how that
Yeah,
influences their choices.
yeah. So for almost all TP applications, I would suggest going and looking at, start from the user interface, start from how the user thinks about your system. And even if we are rendering a lot of tables to the user, at the end of the day, most of the things that we work on today are complex object graphs. When I'm talking about complex object graph, I'm not talking about graph in the sense of social networks or find my friend or something like that. I'm talking about what is the sort of model that I'm working on. And think about what credit card statement looks like, or a vacation request for a user, or an insurance policy, a hospital visit, those sort of things. All of them are really complicated. They are not something that you can easily throw into tabular form and then render back again very easily. In most cases, I love modeling, and again, I'm absolutely biased here, just to be clear, but I love modeling on pen and paper. Here is what this looks like. And I'm looking at this document, and then I need to decide, is this something that I can just take one to one and throw into a document database, or does it make sense to try to throw that into a tabular database, a relational database? And for reporting purposes, I think that relational databases or even dedicated column slash all of databases are still very much the right tool for the job. But the difference here is that my queries are more complicated. I'm working over more data. For transaction operations, I want to touch this specific thing, that thing, etc. And that, I think, fits a lot more closely to the document model. Something that we haven't touched on but is important is that we tend to not just have a single store across our system. So I would have, let's say, if talking about insurance application. So I may have time series data for the heart rate of my users and measure, and then I have the policy document with all of, you have pre-existing conditions of going bald, no hair implants for you, whatever. And again, think about the insurance policy. That is a really complicated structure. Try to throw that into a relational database, and good luck trying to get data out of that. But I also want to be able to search for, have we seen this type of claim before? This guy has been totaling a car every 3 weeks for the past year. Maybe we should stop insuring him, stuff like that. So we're looking at multiple data stores in many cases. You mentioned graph databases, and graph databases in many cases are used specifically to solve graph problems. They wouldn't be the system of store. If I'm comparing Elastic as, again, not a system of record, not where you put the data, but you tend to throw a lot of data into that, and then you maybe use something like Kibana to gather some information out, or maybe try to use unstructured search and just try to discover things on the fly, etc. For the system of record, however, there are different considerations. Whatever this is, transactions, complexity, the ability to query the data, I think, is quite important. Other aspects, when you mention joins across different tables, I want to challenge that statement and talk about, when do you actually need to join between tables? Is it when you're operating over different aspects of the same aggregate route? So if we take the shopping cart and line items, if I want to render the shopping cart, I often need to join to the line items and the product table as well. But if I'm rendering the shopping cart as a document, then I don't need to, I can just say, give me these documents, and I have all of that information directly in. If I now, and I'm going to talk about a specific feature for RavenDB here, and this is something called include. You can say, hey, I want you to look at this document and look at those paths which represent additional documents, and give me this document and give me those related documents as well. In MongoDB, there is something called a lookup, which serves a similar purpose for a join. And the idea here is that you can traverse between documents, even in a non-relational database, but it's not a join. And the reason that include is not a join is that it's not a Cartesian product. It doesn't modify the way that your output behave. In most cases, this operation is applied after query processing. So just before you need, here is a set of results, let's now include, project, whatever, get data from related document, etc. That matters a lot because it means that you don't have to deal with all of the related complexities.
This episode is brought to you by Datafold, a testing automation platform for data engineers that prevents data quality issues from entering every part of your data workflow, from migration to dbt deployment. Datafold has recently launched data replication testing, providing ongoing validation for source-to-target replication. Leverage Datafold's fast, cross-database data diffing and monitoring to test your replication pipelines automatically and continuously. Validate consistency between source and target at any scale, and receive alerts about any discrepancies. Learn more about Datafold by visiting dataengineeringpodcast.com/Datafold today. The latest wrench to get thrown into the works of the database market is, I would say, most people would agree, the advent of generative AI, which has caused virtually every database vendor to say, oh, I now support vectors. And I'm curious what your sense of that is as somebody who's building a database engine. How important is it for the vector to be a native data type and to support the various algorithms that need to be able to operate on those vectors, and just how you see the changing landscape of database adoption, the number of different databases that are out there, and the ways that people are trying to leverage those database engines for new and evolving use cases, and just how you think about that pushing the database market going forward.
I'm going to go out on a limb a little bit here. If we were having this conversation 2 years ago, I'm assuming that you would be asking me about blockchains and the ability to use quantum proof encryption, quantum proof unit of work or something like that. And I thought then, I think now that blockchain is an interesting way of maybe manage money, but it's a really poor database. Vector search, when you think about it, is from a technical perspective. Vector search is a really nice statement, but let's talk about what it actually means. It means that I have some text, I hand that into an NI, and it gives me an embedding list of position in vector, vector of positions, whatever. And then I need to be able to do search me something that is near here across all of the dimensions that they have here. So the algorithm is KNN, K nearest neighbor, sorry, or something like that. So from a computational perspective, this is a very obvious thing. What's the problem? The problem here is that this is really niche to really specific scenarios. Under what cases do you actually want to do a vector search when I want to load the related products for what I have in my shopping cart, so as a recommendation engine, for example? That doesn't happen, and most OLTP systems don't actually need it, and it is amazing feature in terms of, I have generative AI, here is the checkbox on this. But I don't like that. This doesn't actually provide a lot of value for the user. Other aspects is the inscrutability of AI. And that means that if you want almost identical inputs into the system, you're going to potentially get very different outputs. And I find that this makes me quite nervous in terms of predictability, performance, and those sort of things. And finally, what's the actual use case? I mean, I'm trying to think about, I want to build a chatbot. Okay, that's great. How is that related to what you want? I need to be able to summarize finding based on what the user is asking. Well, here is how you do that with not needing any fancy vector search. Take the user question, ask the AI, give me the concrete keywords for what I should be asking on that, and then query over that. That gives you highly predictable, well-tuned system that you can look at as, here is the black box, and everything else is visible to me. And then you take the output of that, and then it says, okay, now I understand. Now here, let's say I'm searching, give me all of the drones that can connect to a Android 7, whatever, and have over 150 height capacity. Okay, great. I can take that, ask the AI to the model to give me the keyword, which is maybe a drone, whatever model is required, etc. And then I search for that on the products, and then I can feed the products to the AI to present that to the user as necessary. And this massively reduces the amount of magic that you have in your life.
I appreciate that answer because it's definitely interesting to get the perspectives of different people for these various hype cycles and how much of it is actually a lasting question that needs to be solved for, and how much of it is just a point in time that has gotten people all excited and it will eventually die down because there isn't any fundamental shift in the ways that the world works. Now, looking to the process of actually designing and building a non relational database engine as somebody who is doing it I'm curious what you see as the first steps on that journey and some of the ways that you think about the initial set of questions that you're trying to answer that will get you to your eventual goal, and how many of those questions you can actually answer as this is the primary functionality that I want before they start to conflict with each other.
It's funny, if you look at database engines, there is at the bottom most tier, you have something called a storage engine. This is how the database actually reads and writes data from the disk. And I find it funny because there is a very popular storage engine called RocksDB. And RocksDB has been used as a storage engine for MySQL. There is something called MyRocks, as well as the storage engine for many non-relational databases. And at the end of it, all databases have to deal with physical realities. I need to be able to search something, so the underlying data structure has to be sorted in some way, and all I have to offer you is some permutation on that. Now, if we look into the actual model, then the network protocol, I mentioned the chatty versus batch transaction models. Am I talking about individual values, and am I modifying them on bulk or not? All of those are really important questions that you have to think about. Am I a good example? Maybe let's look if I want to submit individual queries, or do I submit a whole set of them for the engine to operate on? There is a tremendous number of trade-offs that you have to take into account, and how do you operate on that. I think that when you start thinking about the database design, sitting down and writing a sample application, not necessarily as writing a sample application, but writing the use cases, and then here is the set of endpoints that I have, and here is the interaction. So go and sit and write the SQL that you would have there. Here is the data that I write, here is the data that I read, here is how I do all sorts of things, and that tells you a lot about what you want to do. If I'm comparing, for example, am I interested in running aggregated queries? I mean, if I'm using Cassandra, then the answer is no, because there is no way to actually do that. If I care about running only aggregations, then a column family is a much better choice. If I'm running a streaming data source, then I care about my state and very rapid ability to load a particular state modifier and save it back. Then we have to figure out what is the, I don't know if calling the secret sauce is the right thing, but what is my strong point? What is the thing that people come to me? This is what I need it for, and then everything else comes from that. For Raven, my thought was I want to be boring. I want you to get the data and go do your own thing, and everything revolves around that. Oh, I have to be boring, so operation needs to be simple. I mentioned the count and paging earlier, but that also meant that my modeling had to be simple. So I went with document basis, and you define the model in your code, and it's very easy to change and update over time. If I care a lot about graph traversals and RDF tuppers or something like that, so the question is what's my purpose? What am I trying to achieve? The interesting thing here is that, again, I've been doing it for 15 years, and the initial thing that you start with has a huge impact on your overall design. But over time, you realize that, hey, there are other things that I can also approach and do. So RavenDB has support for managing time series directly inside of the database. Almost accidentally, we realized that we have a document model, and we allow you to write to multiple nodes in the cluster at the same time. So it's not a single primary. Every node can be can accept writes all the time. Oh, what happens if I put those nodes on drastically different geographical locations? And now I don't have just a cluster, I have distributed one. and then also something like that to just start falling down from those early design decisions. And there is a very strong need to make sure that this is generate a cohesive end result versus, I can do this and this and this, but there is nothing that pulls this together. One feature that we ended up implementing was the idea of allowing you to do background processing of a query. So you can write a query and subscribe to these results as a persistent status. And the example I'd like to give is, whenever an order is set to paid, now there is some other process that handles the shipping of that. So I have a query such as from orders where status is paid. And I have workers that are subscribing to this and accept that, and then they are all about being able to reliably process that. This feature actually came about from implementing replication, so I know where is my replication status here on the other node, but I was able to leverage that to implement persistent queries on the other side of that. So there is a lot of impact on those details. If we didn't have the cursor position for replication, we couldn't utilize that same thing for a persistent query cursor at the same time.
The exploration of the evolution of the requirement set is interesting. And as you said, you added the capability for managing time series. Your core focus was just how do I make this boring and easy to use? And I'm wondering, as you have added new capabilities, as customers have asked for new things, as the open source community has tried pulling and pushing the engine in different directions, how have the early technical decisions of how to actually implement and architect the engine hamstrung you in those efforts of evolution and some of the unanticipated challenges and pain points that you've run into in the process?
So the primary issue that we run into when I started writing RavenDB for the first time, I was primarily an application developer. And RavenDB is written in C Sharp, and I wrote it initially as a pretty standard ASP.NET application, which meant the protocol that RavenDB uses is REST-based HTTP calls, etc. And that was a very native way of doing that. And it worked beautifully in the sense that we're able to rapidly get it out and get users and everything. And at the same time, we ended up in 2014 or something like that, we had almost consecutive set of performance problems from users. And you end up realizing that the way that we even approached entire things was broken because we were spending 85 to 95% of our time in garbage collection. So at that time, I remember it was like fighting fires, and you spray some water there, and before you manage to quiet this thing, you have to run over to the other location and spray some more water there. We started having users with 100 gigabyte datasets, and suddenly running a GC on that sort of dataset is just okay. That's expensive, and we generate a lot of garbage to an operation because we never actually policed our location. We just wanted to get the software out there. So in 2015, we actually took a step back and did something that I'm really, really proud of. We sat down and did a postmortem of the entire system. And we said, this is, or here are all of the things that we did badly. What would we do differently if we started it today? And then I did something really stupid, and we basically rewrote the engine from scratch while still supporting the old version. And this was, I'm saying stupid because it took us close to 3 years of old version and new version, and we had to do backward compatibility issue along the way. It was really, really painful. But the end result was an engine that was more than 10 times faster and much easier to work with and extend. And I want to give you one particular example of the major difference that is involved. So RavenDB is a document database. It stores and operates over JSON documents. Now, how do you store JSON documents? The native way of doing that is to just store the JSON text, and then you can operate over that. But then you realize something really, really nasty. JSON is a really poor format if you need to do operations on that, because let's say that I want to say, give me the names of all of the employees in London. Well, I have an index on the city that you're at, and I can start executing on that. Perfect. But now I have a list of all of the employees in London. I need to fetch the name. How do I fetch the name? If I'm using JSON, I need to actually parse the text. That's expensive. And if I need to do another, to get another field, I have to parse another piece of text. So it's actually, in most cases, it's easier to parse the text once into a JSON object in memory and just render it this way. And because I wanted to avoid parsing JSON over and over again, I introduced a cache into the mix. So far, so good. It makes perfect sense. I had amazing benchmark results because of that. Move a few years later, datasets grow, and amount of work that we do has also grown tremendously, and we've seen a lot of issues there. Every time, and the crazy thing here is that when I profile the system, I'm not actually seeing a lot of time spent in JSON parsing. I spend a lot of time spent in GC, and I cannot understand what's going on. And then I realized that the foreign set of events happen. We are running on near to full capacity, so almost no memory. And we are loading data from the disk and parse that, throw that into the cache, and run on board. Now, the process and a JSON object, a JSON document is composed of many different objects. So, and it's basically an object graph. So we deserialize that into an in-memory object graph and stick it into a cache. And the problem then is that the cache gets full, and we are running GC, and this is running, and everything in the cache get pushed into a higher generation. But now I'm about to run out of memory. Well, the cache will respawn and evict something from memory. But this situation basically means that now the cache that I created has turned itself into an evil made process, basically, that would keep the cached values in memory just long enough to push them to Gen 2. So when we actually about to run out of memory, we would have to do a really expensive Gen 2 collection. And one of the things that we did with the new version of RavenDB is to not use JSON internally to store the data. We're using something called Bleatable, which is a zero copy format, which allows you to, we search for a page, we get a pointer, we use memory map files, we get a pointer to the document, and then we can, using just pointer arithmetic, get to the exact name field that you want. No need to parse anything, no need to keep anything in managed memory. Everything is already in unmanaged memory, which means that we can lean heavily on the operating system for memory management. It means that repeated queries on the same thing benefit from the page case of the OS and all sorts of other stuff like that without needing to pay any GC costs. And that was an explicit design decision. I remember it took us like 6 months to a year to get to the point that, okay, now I can test that. And I remember, I know this is going to be bad. We haven't had a chance yet to actually do any major optimization. And I'm comparing that one versus the other. And one of them was able to hit, I think, 3,000 queries per second. This one was able to hit 50,000 requests per second. Like, okay, we really have something there.
You mentioned that at that point where you were running into those performance issues, you effectively had to rewrite the engine from the ground up. with the concept of if I had to do it over today, how would I do it? I'm interested as you stand now that you've gone through that pain and out the other side, if you were to start a new database engine today, what would you build?
Interesting. So an engine today would probably be using the batch transaction model. It would be talking over TCP/IP or Quick or something like that. So with multiple streams. Probably not Quick, however, because of its reliance on TLS. I want to use something that doesn't involve expiring certificates. It would probably be, if I had to choose, that there is a difference between what I think would be a really good database to build from a technical perspective and what would be a good database to build from a commercial perspective. Probably something that would allow me to run on synchronous data to mobile devices and things like that, just because of the wide applicability and ease of use. Other aspects here are would almost certainly be non-relational. I don't think there is much value in another relational database. The distribution model would probably be very different. When I created RavenDB, I was very heavily influenced by the Dynamo paper for Amazon with the issues of concurrent multiple rights and things like that. But the situation today is very different. Would probably have a lot more reliance on cloud technology. So, for example, the way that RavenDB works, we assume that we have a disk to work on. Today, I would say, hey, no, I would probably design something that is based around S3 compatible storage. So my idea is, okay, I have some data and I want to operate on that, and I write a head log, and this is the only thing that needs to be maintained on the disk, and everything else is then throw into S3 compatible or something like that. And that means that you can have native approach to, oh, here's how I read and write across many systems without having to deal with expensive NVMe instances or something like that.
As somebody who has been working in the database ecosystem for a number of years now, you have your own database engine that you build and maintain and work with customers around. What are some of the most interesting or innovative or unexpected ways that you have seen either non relational engines generally or RavenDB specifically applied?
People would take you to the edge and then push. I had a user one time that called me and says that RavenDB is very slow for his use case. I'm like, okay, what's going on? And his use case was a product catalog, and he had something in the order of 50,000 items in the catalog. I'm like, that's weird. That's more than within our capability. What's going on? And he put the entire catalog as a single JSON document. And I had to explain, hey, RavenDB is a document database, but you are allowed to use multiple documents. And a 700 megabyte document that you have to load and parse each time is not the ideal format for what you're trying to do. I have another user who put an array inside a document with everything that happened to a particular scenario. Some scenario may have hundreds of thousands of operations. That's now here is the funny thing. They're reaching to data sizes in the high tens to low hundreds of megabytes for a document. And that means that every time that you operate on that, you have to deal with loss of data. That's not how you want to model things, but it works. Other systems have put limits. So Mongo have a 16 megabyte limit on a document. And on the one hand, I'm happy that I don't have that. I think that we have a limit of 2 gigabyte, which is utterly ridiculous. I didn't think anyone would even approach the hundreds, but people do that. So it's really funny that wherever you have an edge, people will go there. But then again, something that we learned very early on, it's better to be slow than not at all. So think about the scenario where you have a hard limit. Let's say, I think that DynamoDB has a 400 kilobyte limit. That has such huge impact on the way that you design things. Oh, I want to write a blog post. I have a 12-page blog post that I'm writing right now. It does not fit into DynamoDB. Okay, so I literally cannot use this database at all, or I have to restructure everything from the get-go. Whereas, oh, you're running in efficient manner, okay, fix it, but it's not critical. I think that's the thing that I'm also from this. Other thing is RavenDB has a way where you can define index operations that not just index this field, but also run this computation. And at some point, people hit limits that they didn't know we even had. For example, someone put a computation in RavenDB that would generate an invalid program exception. Why is that? They had higher than 65,000 local variables in this computation. I'm like, I don't even have a way of responding to you. You send me this index definition, and I'm in awe that it even got started working. Don't do that sort of thing. So I think the sort of thing that people would put you to use is just flat out amazing.
And in your experience of building RavenDB, working in this ecosystem, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
If it can happen, it will happen. Just to check, while I'm talking to you, I'm working on a system that has 4.1 gigahertz CPU, which means that on every one of the 12 nodes that I have available, I can do 4.7 billion operations per second. If you say 1 in a million, it's right now. We run into any source of race condition in my code, between my threads, between distributed systems, and it's just really, really strange to see that. One of the best investment that we did is generating additional information about how the system is working, what's going on, those sort of things. Beyond that, correlation is something that would stop you in a way I cannot even explain. We had a bug. That bug was initially written in 2013. In 2024, we had 4 separate issues within the span of 2 weeks, all of them exposing this bug from several different customers. I'm like, okay, yeah, I get this is a bug. We'll fix that. But how come no one ever found that in that amount of time? That's utterly ridiculous. And now 4 different people, unrelated to one another, found it at the same time. And that's something that we saw happening over and over again. We had Windows 2016 and lower have a global lock for the page table. So, okay, if you do things just right, you can spend 90% of your time in kernel mode. I've been running Raven since 2009. So the actual product was in existence in 2000, not just design. And we discovered that bug in 2020 after 2 separate customers came to us within the same team about this thing. How come we never figured this one out before? And then you realize that, oh, you have to have these 6 different things happen all at once in order for this to actually trigger. And okay, I understand that. So how come it triggered now? I have no way of explaining that.
Yes, the interesting laws of probability where you see something and you say, "Oh, that's super rare. I don't have to worry about it." But then you start to operate at scale, and that rarity happens all the time. Similar to the issues that Google and Amazon run into with hard drive disk failures, where if you run enough hard disks for long enough, you're going to be failing all the time. For people who are looking at selecting a database engine, they're trying to decide what exactly they need to use to solve their particular use case. What are the situations where a non-relational engine generally or RavenDB specifically are the wrong choice?
If you're running a reporting database, most non-relational systems are probably not a good idea. If you have a relatively small amount of data and huge variance in the way that you query that, so that's probably SQL is a really wonderful language, and the sort of things that you can do from a relational engine can be quite amazing. But the funny thing about it is, as your system grows, the number of operations that you're doing reduces because you would have the transaction database and the all-up database and the reporting database, and here you have the here it goes to Kafka to do stream processing, etc., etc. So try to select something that can cover your scenarios. At the same time, there used to be the case that everything needs to be a separate microservice, and now you have the monster is called a distributed monolith. So trying to fit everything into a single location, especially if it's a bad fit, like complex object models inside of relational database where you have to stitch them together all the time using joins, is a bad idea. But in the same sense, is trying to get a non-relational database to do relations. And this is really, really common. One of the things that we struggle with is users who build their models as if everything was still in a relational table, and then they can't figure out how to code themselves out of this situation.
And as you continue to build and iterate on and evolve the RavenDB engine, what are some of the things you have planned for the near to medium term, or any particular projects or problem areas you're excited to explore?
So I consider RavenDB now to be a really mature database. So we have all of the features that we want to have in the database. What we are looking now is into the ecosystem and whatever this is. Okay, let me show you how we can integrate with actor frameworks in order to make your life easier, how I can plug into additional elements in your environment. So using Kafka. So here is how RavenDB can pull and push data from Kafka natively without you needing to write your code. Here is how you can distribute your data to and start using serverless more easily with RavenDB, those sort of things in the sense of, okay, you threw the data in, what do you do with that? And we want to ensure that we have a good answer for whatever you want to do there.
Are there any other aspects of this space of non-relational databases, the design and implementation of them, and their applications for end users that we didn't discuss yet that you'd like to cover before we close out the show?
I don't think so. I would like to recommend Building Data Intensive Databases, which is a great book. And if you really care about how databases are built from the inside out, there is another great database called Database Internals. None of them are my book, by the way, which is a really deep dive into how databases are built from the inside out, both for local databases and distributed ones.
Yeah, I'll second the recommendation of designing data intensive applications. That's a very well written book. I learned a lot from it. I will have to take a look at the database internals book. And for anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. As the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Where is your data, and where is your data is located, and where is it going? Just I think that for most enterprises, just understanding that is a huge challenge. If I'm talking about, I have a customer coming to my system, where is it located? what database is where it's located, and especially when you put in data governance, GDPR, those sort of things, this is a huge, complicated task to deal with, especially as your system grows, and just traversing what's going on can be an incredibly challenging task.
Absolutely. Well, thank you very much for taking the time today to join me and share the work that you have done on RavenDB, your expertise on the ecosystem, and your insights into non-relational database engines and their design. I appreciate all of the time and energy you've put into helping to move this space forward, and I hope you enjoy the rest of your day.
Thank you very much. Thank you for having me.
Thank you for listening. Don't forget to check out our other shows, Podcast.init, which covers the Python language, its community, and the innovative ways it is being used, and the Machine Learning Podcast, which helps you go from idea to production with machine learning. Visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.